All right, let's dive into something fascinating. We live in a world that is just drowning in data, right? So how in the world do we find the needles in that gigantic haystack? How do you spot when two things are similar when you're dealing with literally billions of items? Turns out there's a really, really clever shortcut for that. I mean, think about it for a second. Every single day, a flood of new articles hits the internet. So how does a search engine possibly know that one article is basically just a copy of another? When you think about the scale, it seems like an absolutely impossible job, doesn't it? And that really gets to the heart of it. The real challenge here is just the insane scale of the data. We can call it the billion item problem. Because when you're playing with numbers this big, the obvious, straightforward approach just completely falls apart. Look, if you had a billion web pages, the simple way to find duplicates would be to compare every single page to every other single page. That's a billion times a billion comparisons. We're talking about a number with 18 zeros after it. Even with the fastest supercomputers on the planet, that wouldn't just be slow. We're talking centuries. No joke. We need a totally different way to think about this. So, okay, before we can find similar things fast, we first have to get on the same page about what similar even means. We need a clear mathematical way to define it. And for that, we're going to use a cool little metric called Jaccard similarity. It sounds kind of fancy, but the idea is actually super intuitive. You just take two groups of things, say all the unique phrases in two articles, and you divide the number of things they share by the total number of unique things between them. That's it. Let's make this real. So we've got document A and document B. You can see the stuff they have in common. What we call the intersection is 3 phrases. And if you count up every unique phrase across both documents, the union, you get a total of 6. And from there, the math is a piece of cake. You just divide the intersection, which is 3, by the union, which is 6. That gives us a similarity score of 0.5, or you could say they're 50% similar. It's a perfect logical way to measure this. But, and there's always a but, right? Here's the big catch. To get that perfect score, we still had to read both documents from top to bottom to figure out what they share and what they don't. So we've got a great definition for similarity, but we haven't solved our speed problem at all. We're right back where we started. So how do we get out of this mess? Well, this is where things get really, really clever. We're going to use an amazing trick, a kind of algorithmic sleight of hand called a MinHash signature. And this is the profound idea right here. What if, instead of comparing these huge, clunky documents, what if we could create a tiny, compressed fingerprint for each one? A signature so small that comparing them would be almost instant, but so cleverly designed that it still gives us a pretty good guess of the true similarity. Okay, to do that, first things first, we need to translate our documents into a language a computer can chew on. We build a matrix, just like this one. Every column is a document, and every row is some unique phrase or word. A 1 just means, yep, this document has that phrase, and a 0 means, nope, it doesn't. Now for the magic trick itself. Conceptually, it's just 3 steps, and it's simpler than it sounds. First, just imagine we randomly shuffle all the rows. Just mix them all up. Second, for each document, we're going to scan down this new shuffled list. And third, the instant we hit the very first one, we stop. The number of that row, that becomes our signature. Okay, let's actually see this happen. On the left, you've got our original matrix. On the right, the rows have been completely reordered based on some random permutation. Now we just scan down each column on the right, and we're looking for that first one. The original row number where we find it, that's our signature value. And boom. After that whole process, look what we've got. An entire document, that whole column of 1s and 0s, has been squashed down into one single number. Think about that. We can do this with a few different random shuffles to get a more reliable signature, but the core idea is this incredible compression of data. Okay, that's awesome. But you might already see the next problem, right? Actually shuffling billions of rows, even inside a computer, is still way, way too slow. So now we need a shortcut for our shortcut. And the solution is just as brilliant. It turns out we don't have to actually shuffle anything at all. We can use a neat mathematical tool called a hash function to simulate the random shuffle. It gives us the exact same result, finding that first one, but without doing any of the slow, painful reordering. It's pure mathematical magic. Now, in the real world, you wouldn't just rely on one hash function. That's a little risky. Instead, you use a bunch of them. Here you can see we've used 3 to build a richer, more dependable signature for each document. So now, document S1 isn't just one number, it's represented by the signature 101. This makes our comparisons way more robust. So, the million-dollar question, did it actually work? Is our shortcut any good? Well, let's just compare. On the left, you see the true similarity scores, the ones that are perfect but take forever to calculate. And on the right, those are our estimates, based only on those tiny little signatures. Now notice they're not identical, but they tell the same story. They capture which pairs are close and which are far apart, and they do it at a tiny, tiny fraction of the cost. And that right there brings us to the final, and maybe the most crucial, idea in this whole process. It's all about a fundamental trade-off, the trade-off between getting a perfect answer and getting a really useful answer really fast. You see, the fact that our estimate isn't always perfect isn't a bug, it's a feature. The real power of this whole method, it's called locality-sensitive hashing, by the way, is that we get to be in the driver's seat. We can actually tune the parameters to control that balance between speed and accuracy. This chart shows you that control in action. It's amazing. It shows the chance of making a mistake, a false positive, for 3 different settings. Look, if you use a lenient setting, your error rate is over 60%. Not great. But just by tweaking those parameters, making them stricter, boom, you can crush that error rate all the way down to just 7%. So what's the bottom line here? It's that how we structure these comparisons, it matters a lot. That stricter setting isn't just a little bit better. It is more than 8 times better at correctly rejecting pairs that aren't actually that similar. We have very precise control over the outcome. You know, when you step back, what this whole technique really teaches us is one of the biggest lessons in all of modern data science. When you're dealing with problems at a global scale, sometimes chasing absolute perfection is the enemy of getting anything done at all. Trading a tiny bit of accuracy for a mind-blowing gain in speed is what makes so much of our digital world possible. And that's the thought I want to leave you with. This whole idea of approximation, of trade-offs. It's not just for computers. So ask yourself, where else, in your work, in your life, in society, is a good enough answer that you can get right now infinitely more valuable than a perfect answer that might never arrive?